Woohoo, we are live. This is Math 40 Elementary Algebra, and this is 3.2. We're going to be graphing linear equations. Woo! And no spoilers, but the word linear comes from the word line. So really what we're graphing today is lines, and so make sure you have a ruler of some sort, and make sure you also have either print out these notes, in which case I've given you a grid that you can use, or if you don't have a way to print this out, try to get a hold of some graph paper. For this class, you won't need many pages. You can get away with, maybe a dozen pages if you use them carefully. But these are really important because when you use these to graph, your graphs will be much more precise. The lines will actually be straight lines. If you just use lined paper, you don't get the same practice. And then when you are in the future asked to do math on grid paper, you won't have had the practice. So do try to get some graph paper some way. Okay, let's get started. So the first problem is we've got an equation, y equals x plus 1. And the instructions are to list pairs of numbers that satisfy this equation, so x and y, and we're supposed to construct a table of values. So there are a couple ways to do a table of values. One way to do a table of values looks a little bit like this. This is a kind of a fancy way to do it. And then what I generally do is you pick one or the other and you pick a number, just a number at random. I'm going to pick 0 for x because I always start with 0 because it's usually pretty easy. And then y is equal to 0 plus 1, which is 1. So that corresponds to the ordered pair 0, 1. Now, I will point out there is another way to do a table of values. It's a lot more streamlined, but you don't show your work. So you're going to have to do your work in your head or somewhere else. If x is 0, y is 1. So you just list the numbers, or you could list all the work. It's up to you, your choice. Okay, I'm going to roll. I'll try x equals 1. So y equals 1 plus 1, right? Because every time I have an x value, I plug it in there for x. So it's going to be every time whatever the number is there goes there. That number goes there. Okay, so 1 plus 1 is 2. Or if you're doing the streamlined version, it would be 1 and then y is 2. And that corresponds to the ordered pair 1, 2. And you don't have to write both of these. I'm showing you the two different options. If x is 2, y is 2 plus 1, which is 3. Or you could just list them as 2, 3. I should try some other numbers just to get some other interesting numbers. -1, y equals -1 plus 1. We have to think about that. -1 plus 1, that's 0. So I've got the ordered pair -1, 0, which I can write like that as well. And then I could try a 1/2. 1/2 plus 1. Well, that's 1.5, which is 1.5. So I could switch to decimals and do 0.5, 1.5. Oh no, I've run out of room. 0.5, 1.5. Okay, now the next question I'm going to have for you is, and your table of values could be really different. You could have completely different numbers. But when would I have to stop? How far would I go before I get all the points? And the answer is you would never be able to stop, because am I going to run out of numbers? Nah, there are an infinite number of numbers. There's a lot of them. Infinity is really something I think humans have a really hard time understanding, but it's a lot. It's a lot of a lot. And so I could keep coming up with numbers. Now, some of the numbers I'd come up with are hard to graph, like 400 million would be hard to graph. X would be 400 million, Y would be 400 million and 1. You got it. But I would not actually have to ever stop in my lifetime or my kid's lifetime or their kid's lifetime, et cetera, et cetera, et cetera. So this could be a very long table of values. And I'm not sure that this all really gives me a good image in my head of what's really going on with this equation. I would love to be able to kind of summarize the information better. So the table of values are nice. The list of ordered pairs are nice. But what I'm really going to do is I'm probably going to graph. So I'm going to put that on the back burner though, because we've got this question, which oddly enough says C. And I think that was a typo. Sorry about that. That should say A or B. Or you know what? Let me just say, oh, look, is that a pteranodon in your house? Why didn't you guys turn around and look over there? Okay, there we go. What? I was wrong. I guess it's not a pteranodon in your house. Okay, does 4, 4 satisfy that equation? So that means x equals 4 and y equals 4. Let's try it out. So I've got y equals x plus 1. This doesn't seem likely, but let me try it. Does 4 equal 4 plus 1? No. Okay, how about 5, negative 5? Let's try that one. 5, negative 5 means that x equals 5, y equals negative 5. Let's try that. Y equals x plus 1, negative 5. Does that equal 5 plus 1? Okay, 5 plus 1 is equal to 6. No. So now I want to ask you, how many points are there that don't satisfy? So how many ordered pairs are there that don't satisfy this equation? And the answer is even more than do. Most ordered pairs will not satisfy this equation. You got to get lucky to land on one of these special ones. So this is going to be really, really a painful process. So at the bottom, I say, rather than checking by hand, wouldn't it be great to have a way to quickly determine whether ordered pairs are solutions? And you guys all say, yeah, that sounds great. Let's do it. Thank you, mathematician. Why, you're welcome. Okay, so my order, oh, you know what? I didn't want to put that underneath. Sorry, got excited. We were going to do math. You know how when you're about to do math and you get really excited, as you do. It'd be that way sometimes, you know? Okay, so I'm going to start off with, I'm taking a look at these values. I don't see any exceptionally large values, exceptionally small values. They seem pretty straightforward. I've got a lot of room. So I'm just going to go ahead and put my axes in the middle. Now, sometimes what you do is you put your axes a little over to the left or the right or the top or the bottom, so you've got more room in one of the quadrants. But these quadrants don't seem to need, I mean, I don't need a lot of room. I need to get up to the number 5, I think, or 3, 4. Not that high, so we're okay. Okay. Arrows, arrows, X, Y, arrows, arrows. There we go. Okay, so see how pretty it is? It's so pretty. We're going to plot these pairs on a rectangular coordinate system. I'm going to set my scale 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. You don't have to write them all in. 1, 2, 3, 4, 5. I'm just doing it because, yeah, it's habit. And also, I think, especially when you're starting out, it's helpful. The less you have to do in your head, the easier math is going to be. At least for me. Okay, so I've got the following ordered pairs. I've got 0, 1, which means x is 0, y is 1. So x is 0, y is 1. It's right there on the y-axis. 1, 2. So I go out to 1, and then I go up to 2. And then I've got 2, 3. So I go right to 2 and up to 3. And already I'm noticing a pattern. -1, 0. So I go over to -1, but then I don't go up or down. I just stay there on the x-axis. Okay. And then 0.5 or 1/2 and 1.5. So I go over to 1/2, and I have to kind of estimate this, and I go up to 1.5. Now, what do you notice about all the points? Yeah, they all seem to lie on a line. I mean, all of them. And in fact, if I draw this line in, and then I go looking, I wonder, that's a point that's on this line, and that point looks like it's at x equals -3 and y equals -2. So let's check that. -3, -2. Does it satisfy the equation? Y equals x plus 1. So is -2 equal to -3 plus 1? -3 plus 1 is -2. Yes, it does. Okay, so that's interesting. So a point that we didn't come up with over here, but which I can just see on the graph, works out. Let's try another one. This one is up here. What's that one? Okay, x is 4 and y is 5. So this is 4 comma 5. I can already tell. 4 comma 5. If y equals x plus 1, I've got 5. Is that equal to 4 plus 1? And the answer is yes, it is. So what is the cool thing we discover? I wanted to double check that I hadn't said it on the next page before I write it down. Here is this I give to you. This is the fact. For a linear equation, we're going to talk about what that looks like. But for a linear equation, you ready? Let me bring this up kind of central. Every solution lies in or on, depending on your perspective, a straight line. Every point on that line is a solution. I'm running out of room, so I'm writing solution in the weird mathy ways. SOL with an N on top of a line is solution. So in other words, if you came up with a completely different set of numbers for your table of value, your points would not be right where I graphed mine, but they would all lie on that same line. And if you extend this line as far as you want, any single point, all the points on this line satisfy the equation. That's part of what makes it linear. It makes a line. So now what's a linear equation? Well, the silly answer, the easy answer is it's all the equations we will give you in this chapter. And that's a really terrible answer. But basically, what a linear equation is it will have usually a y and an x. And you notice how neither one is squared and neither one is square rooted. Neither one is in the denominator. So you get a plain y and a plain x and some numbers. You've got a linear equation. You even have a linear equation if you have just a y and some numbers or just an x and some numbers. So as long as you've got plain x and y or one or the other, you've got a linear equation. So now, what can we do with a linear equation? Well, we can graph them, and we will. We will graph every linear equation there is on the planet. It'll feel like that by the time we're done with this chapter and you guys are done with your homework. So let's talk about how to approach this. So I've got 2x minus y equals -3. So is this linear? And the answer is yes. And how do I know again? Well, there's an x, there's a y, and the x and the y are not squared. They are not square rooted. They're not in the denominator. They are not, I can't think of anything else that would be weird that you guys would know about. But basically nothing weird's going on. There's just plain x and plain y. Yes, y has a minus sign in front of it. That's fine, still linear. So yes, this is linear. So first step, we have to solve for y. Fun fact, you don't actually have to solve for y to do this problem. It just makes it easier. That's why I'm suggesting it. Okay, 2x minus y equals -3. I'm going to be lazy, believe it or not, and I'm going to recommend we add y to both sides. If you would like to move the 2x over to the right, that's fine. Go for it. I'm going to add y because I really don't like negatives. So again, remember, because we were a little rusty with the solving equations. Make sure if you put your pen or pencil on the equals sign, there's a plus y on either side. Okay, I get y minus 3, and then I'm going to add 3 to both sides. 2x plus 3 equals y. Okay, or could I write y equals 2x plus 3? So just flip the whole thing around. What do you guys think? Kind of woohoo? Okay, now I'm regretting that I put this in the middle. Not very good use of space. But let me see if I can squish in a table of values right here. There's my x. There's my y equals 2x plus 3. So it's going to be a little bit of work. But let's start with 0. When x is 0, y equals 2 times 0 plus 3, which is 0 plus 3, which is 3. So I've got a point 0, 3. So I'm going to write that down here. That's one of my ordered pairs. Okay, let me try x equals 1. Y equals 2 times 1 plus 3. So that's 2 plus 3, which is 5. So 1, 5. Okay, 2. Y equals 2 times 2 plus 3. That's 4 plus 3 equals 7. And at this point, are you seeing a pattern? Because I'm seeing a pattern. As x is increasing by 1, y is increasing by 2. That's interesting. And there is a 2 in the equation. Let me try the next one. If it follows, the next one should be 3 comma what? Should be 3 comma 9. Let's see if it works. 2 times 3 plus 3. 6 plus 3 is 9. It is. Notice there's a pattern. Now, these points might be a little hard to graph, so I'm going to be really careful about this. I'm also going to try -2, just for the heck of it, because you should try different kinds of numbers just to see what interesting things are happening. 2 times -2 is -4, plus 3 is -1. So I get a point -2, -1. Once you get enough points that you feel confident, let's figure out, okay, y is going to have to go from -1 all the way up to 9. I think I'm going to regret myself. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, interesting. So I gave it 13. So notice what I'm going to do. I'm going to put my x-axis down low. Down there. You can choose to put yours wherever you like. Now the x values don't get very big or very small. So I'm going to put my y-axis. Notice that if my y-axis my y values get big, I have to put my x-axis low. If my x values get big, I would have to put my y-axis carefully. But I don't have to in this case. Glasses are coming off. You know it's serious when the glasses come off. Okay, there's my x, there's my y. Make sure you've got arrows. Make sure you identify your x and y axes. I know we all assume that's going to be like this, but you really, really, really want to write it in. It's good practice. Okay, I'm going to use the standard, and I'm going to show you a slightly different way to show scale. So this is kind of stylized, but one way to show scale is just to write in like the 5s if you wanted to. So +5, -5, 1, 2. Wait, 1, 2, 3, 4, 5. Yes, that's good. 1, 2, 3, 4, 5. Excellent. Okay. So, and in fact, 5, 6, 7, 8, 9. Here's 10. I'll put 10 up there. So you don't have to write in every number. This is another suggestion for style. You can write in every number, but if you want to write just a few numbers, it's kind of a cool way to do it. Okay, 0, 3, which means nowhere in the left and right. So I start at 0, but I go up to 1, 2, 3. There's my 0, 3 point. Okay, 1, 5. Here I go right 1 and up 5. 1, 2, 3, 4, 5. There's my second point. Okay, 2, 7. 1, 2, 1, 2, 3, 4, 5, 6, 7. There we go. 3, 9. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice so far so good. Those are in a line. -2, -1. So to the left, -2 to -1. Okay, let me get out my handy dandy ruler. And ta. Now pens are a little tricky. And using ruler with pens, I'm not terribly good at, but keep in mind if the tip of your writing implement is thick, it'll be hard to draw the line right on the points if you're not careful. So, and I think part of it is when I was little, I was not allowed to use pen for math. They told me that I couldn't. It was not allowed, that I was not that perfect. And I was like, well, you're not that perfect either. And then I got in trouble. But yeah, I really like using pen. It's much more clear for me. What do you guys think? We got a line. Congratulations. That's really awesome. Now I'm going to label this as 2x minus y equals -3 so that everyone can, looking at the graph, sees it. And then again, let's review. What does this line mean? This line means that any point, like this one right here, it looks like I've got a point -1, 1. So if we plug in -1 for x, that's -2 plus 3 is 1. Yep, that point is on the graph. So any point on this graph satisfies this equation, which is also this equation. They're just two different versions of the same equation. And any two values that satisfy this equation will be on this line. So that's it. We've drawn a picture. This is the solution set of all pairs of numbers that satisfy this equation. Let me write that out because that is profound. This line represents the entire solution set of pairs of numbers which represent, wait, this line represents the entire solution set of pairs of numbers which satisfy the equation 2x minus y equals -3. Woohoo, woohoo. You guys, we did it. Yay, thanks for hanging out. Thanks for making it through. Next up, more graphing, right? Yay. Okay, math on, guys, math on.